GDI in Rochester, New York, and Eindhoven, Netherlands. Rob Anstey is presenting on roll-to-roll manufacturing of 100% silicon anodes. The floor is yours. Many thanks, Rob.
Great. Thanks so much, everybody, for having me. Really look forward to this event every year. Just today, we're going to talk to you about some of the updates on scaling our 100% silicon anodes and how our unique architecture is helping to enable pure silicon in lithium-ion cells. Really, if you look at the market today, it is segmenting into three main categories. There's the low performance, low cost, which is graphite LFP or sodium ion. That you can see the main dominant players are companies like CATL and BYD. And I believe that they will stay the main and dominant players in those categories. Then there's the medium performance, medium cost, which is 100%, 10% silicon, 90% graphite, and it's some sort of NMC, NMCA, NMC811. Some people are even looking to blend some of the next generation LMFPs. But for the most part, it is a nickel-containing cathode. And the dominant players there are LG, Samsung, Panasonic, SK, and others. And then last but not least, where the door is still open for next generation startups, such as GDI and others, is going to a silicon dominant or a lithium metal or maybe a solid state battery. So, and that's really, we're going to see an increase in energy density and maybe changes in terms of safety. What I would say to everybody is that North America and Europe really have to focus on that high performance segment. I think we're seeing a lot of the prices coming out of China on the LFP, and I just don't believe that North America and Europe can win a price war with the costs of LFP cells or the upcoming sodium ion cells from CATL. So we really have to focus on next gen performance in terms of the anode specifically. So the EV companies, for the most part, have come to the same conclusion. Everyone's talking about adding silicon to the anode to some degree. And what you'll hear over and over again is one of the key reasons for this is range. They want to get the extra range. They want to get the faster charging. And in order to get range and fast charging, you have to do silicon, because the problem with lithium metal, for example, is if you try to charge lithium metal quickly, you will find that you form dendrites or mossy-like structure, and that will dramatically reduce your cycle life. So really, out of all the anode materials, silicon seems to be the one material that can increase energy density and fast charging. And that's what we really need to finally hit performance parity between electric vehicles and internal combustion vehicles. Whether it's cars, micromobility, or even aerospace, we really need to continue to increase energy density so that you actually have performance parity, which means, for example, an electric vehicle that gets 500 miles of range and an electric vehicle that you could charge 250 miles in 15 minutes. Once you have something that does that, every driver would be willing to switch over. But look, I drive an EV. I often talk to drivers at charging stations and other about what I think of owning an EV, what I think of driving an EV. And the thing I hear over and over again is, you know what, until it has longer range and faster charging, I'm just not willing to give up my gas car. And I understand that. And that's why, if you notice, most of these OEMs are saying that they want cell level energy of 900 to 1,000 watt hours per liter, because in a car, in a plane, in a drone, in a motorcycle, in order to get that long range in the confined space that you have, you really need to get up towards the 900 to 1,000. If you go back, that's the exact number Mercedes said. That's the number Panasonic said. Tesla really wants a 600-mile car. So the common denominator there is you need the higher volumetric. And on top of that, you really need something that's abundant, low cost, that can charge fast. And that's, once again, why silicon is the answer. Now, there are three main issues with silicon. Otherwise, we'd already all be converted to 100% silicon, right? And that is delamination, particle cracking. Silicon stores so much lithium, it will expand and contract by over 300% volumetrically, which, as you can see in these images to the right, that was a coin cell with a 4 milliamp hour centimeter squared silicon composite coating. So that's silicon and carbon and binder and carbon nanotubes. It ripped the copper to shreds, as you can see. It delaminated from the copper. It basically